the recording and live streaming and let me know that it works.
All right, I think we're good to go.
Okay, thank you. So I'm Noga. I will be the chair for this session. This is the session on coding and information theory. We have four amazing, really amazing talks. So you may know the rules. We have very limited time, only 10 minutes per paper, approximately 5 minutes for talk and then 5 minutes for questions. I will not alert the speakers. It's your responsibility to finish in 5 minutes. If you don't finish, I will do my best to cut you off. And then we'll move to questions. Questions, you have two options. Either you use the questions and answer feature that is on the bottom of the screen, or you just raise hands. All the questions will be at the end of the session, at the end of the talk, as much question as we can. If it's a simple question, I may take the freedom to answer myself. That's it. Okay, so our first speaker will be Amir Shesabi, and he will talk about optimally resilient codes for instead codes that are least decodable from insertions and deletions. Please start.
Right. Thank you very much, Noga, and thanks everyone for tuning in. My name is Amir, and as Noga said, I'm going to talk about optimally resilient codes for least decodable insertions and deletion codes. This is a joint work with my advisor Bernard Heupler and Venkat Guruswamy. Let's start with just a general description of the problem statement. We are going to generally talk about error correcting codes that correct from insertions and deletions. Again, you have like this general setup of Alice having a bunch of symbols out of some alphabet that wants to send through to Bob. But the channel in the middle of these two is suffering from insertions and deletions. And here is just a very quick example of how insertions and deletions would look. Deletion is just eliminating the symbol without putting anything in its place. And insertions can, would be inserting a symbol in the middle of the string, shifting everything after that 1 unit forward. And similar to ordinary error correcting codes, insertion deletion codes are just some subset of strings of length n over the given alphabet sigma. And the quality that we're looking for here is to be able to decode from some delta fraction of deletions and some gamma fraction of insertions. So if you think of a ball of radius delta and delta deletions and gamma insertions around your code words, you want these things to be mutually exclusive. And again, the notion of rate would be defined in the same way that is defined for ordinary error correcting codes. Now, in this work, we particularly focus on least decodable insertion deletion codes rather than the ones that are uniquely decodable. Just to give a general idea of what least decodable codes are, here, instead of looking for being able to uniquely decode the code words the code word that was sent by Alice, we are relaxing this constraint by assuming that it's good enough for Bob to come up with a list of L code words that guarantees to contain what Alice has sent to him. Combinatorially speaking, this would translate into having no more than L code words in a ball of radius delta and gamma in your set of code words. Now, a very natural question that pops up here in this setting is that what is the rate distance trade-off? Basically, if I give you a specific value of delta and gamma, what would be the highest rate of communication rate that you can achieve for least decodable insertion deletion codes? And the answer would look like this. It basically would be a plot. If you have a value for any pair of delta and gamma, of course, the value is 1 when you have no insertions or deletions, but as the amount of, the fraction of errors increase, the rate would drop. And it would be very interesting to figure out how this plot exactly looks like. Now, in this work, in an attempt to address this problem, we started thinking about the error resilience. Now, in general setting of error correcting codes, error resilience would be the largest fraction of errors that you can correct from. Here, it would really translate into, where this plot would hit the floor. What are basically we're asking the question of what is the set of all gamma and deltas where you have positive rate insertion deletion codes that are list decodable from delta and deletions and gamma and insertions. And in general, we are interested in cases where the list size is only polynomially long in terms of n. And so what this work is trying to find is how does that red curve on the floor look like? And just to give you a sense of what this means, when this curve hits the x-axis or like the axis for insertions, that quantity would be the largest fraction of insertions that you can correct from. So that's the error resilience for insertion-only codes. And same on the other side for deletions. Now, there are some easy tricks to identify these plots. Like if I have 1 minus 1 over q fraction of deletions, I can basically eliminate all symbols, all the like q minus 1 least frequent symbols. This means that the delta 0 is less than 1 minus 1 over q. Same if you have like q minus 1 fraction of insertions, you can basically turn any string into n repetitions of 1 to q. So we have these basic bounds on delta 0 and gamma 0. And some previous work have also like tried to find bounds on these things for the specific case of binary codes. But in this work, what we do is we basically not only identify exactly how that red plot looks like, but also give explicit efficient codes that are list decodable from any pair of gamma and delta, any like pair of gamma and delta insertions and deletions in that region. Just to give you a sense of how this would look like, let's say instead of like 1 minus 1 over q fraction of deletions, you have like I over q fraction of deletions. With this, you can basically eliminate the least frequent I symbols of the alphabet. And then you can do the other trick that I talked about. If you have q minus I1 is minus 1 times the length of the resulting string of insertions. This, just this simple argument would eventually show that you have a bunch of points that you would know that are infeasible, that will lie in a second degree curve. Just to summarize the result of the work, what we show is that the error resilience region for insertion and deletions actually exactly fit the polygon that is made out of these points. So here are two like quick examples for the binary case. The region is actually a triangle between delta 0 equals to 1/2 and gamma 0 equals to 1. And for q equals to 5 for alphabets of size 5, it would look like this polygon that I plotted over there. That's basically what the work is presenting. Now, I don't have the time to like tell you how, but it's available on the video. That's uploaded.
Okay, thank you. Thank you for being almost on time. I know it's very hard, this time limit. Any questions? I don't currently see any questions. Right. So I would like to ask, so seems like you solved completely the main or one main open question about incidental codes in list decoding models. What do you view as open problems? Are there open problems that are still left? I know that unique decoding is like a big open problem. Do you think your work can help for that, or are there any other?
There are a couple of important questions. Well, one thing would be answering the same question for uniquely decodable codes, and that has been an open problem for a really long time.
Do you think your work can help with that, or?
I'm not sure, but there is another open question that this might help, and that's like if you remember, like we have this plot of like how the rate should look like, and what we have identified is basically where this plot hits 0. Now this automatically gives an upper bound, like a linear upper bound, if you project like where this plot hits 0 to the 0, 0, 1 point. That will be an upper bound of, this trade-off. But exactly identifying this would be an interesting open problem. Any kind of lower bound, there are a number of lower bounds and upper bounds available, but improving upon them would be a very interesting.
Like understanding the exact rate.
Yeah.
That's what you mean. Mm-hmm. Mm-hmm. Good. Are there any other questions? So Paul Bean is asking, are the codes you construct efficiently list decodable? You have an algorithm that is polynomial time for construction and also for decoding?
Yes, also efficiently decodable, encodable and decodable.
Very cool. Are there any other questions? Salil Badan, can you say a bit about how the codes are constructed? Just a bit, 1 minute.
Just under 30 seconds. So we basically, what we do is we use a code concatenation scheme. For the inner code, we use codes like this. The code words are basically repetitive stretches of zeros and ones with different frequencies. And the frequencies have to form like a geometric progression. There should be like multiplies of each other. And you can show that these codes were presented by Book and Ma. You can actually show that these codes are almost optimally resilient. But the problem with these codes is that like they have very small rate. And then in the second step, we concatenate these codes with some good list decodable install codes that were found in the previous work. And this is basically how the code is constructed.
Thank you. Okay, I'm afraid we will need to either continue on Slack, or I think it's beautifully explained in the talk. I've seen it. So we can continue there. Cool. Okay, so the next speaker, so our next talk, so our next speaker is Sean Shengwan.
Hi. Yeah.
You are here, great.
Yes. Okay.
And Sean will tell us about a really surprising and completely new approach to list decoding of Reed-Solomon codes beyond the Johnson bound. Go ahead.
Okay. So hello everyone. Thank you for being here. I will talk about combinatorial list decoding of Reed-Solomon codes. This is based on a journal work with Zaki Tamo. So for a real number row belongs to 0 and 1, and a positive integer L, a code C is called low comma L list decodable. If for any vector X, the Hamming-Ball of radius low n and the center X has at most L intersections with the code C. So we further call low the decoding radius and L the list size. It is well known that the code word of an NKRS code is given by the following length vector f of 1 to f of n, where the fi's are n distinct elements of the field and f is a polynomial with degree less than k. So we are interested in the following basic problem. Given the code rate r equals k over n and the list size L, how large can low be? So the celebrated work of Goswami and Sudan states that if the decoding radius does not exceed 1 minus square root of r, then one can efficiently list decode RS codes up to this radius. And this radius is commonly known as the Johnson radius for Reed-Solomon codes. So as RS codes are very important in both theory and practice, so it has been a fundamental open problem in the field to determine whether RS codes can list decoded either combinatorially or efficiently beyond this radius. This problem has been open for many years until recently. A breakthrough of Rujal and Wouters showed that one can in fact exist RS codes that can be list decoded beyond this radius, but there is still room for improvement. First, the rate for which they can beat the Johnson radius goes to 0 as the alphabet size Q increases. So basically, they beat the Johnson radius for the low rate. Second, they provide no explicit construction of such codes. Last, the construction is not optimal in the sense that the relation of code rate, decoding radius, and the list size is not tight. Fortunately, in a recent work with Zaki Tamo, we provide two constructions of RS codes that overcomes all of the three shortcomings mentioned above. Our first construction states that if Q is as large as an exponential power of n, then almost all RS codes are 2/3 times 1 minus r, comma 2 list decodable. So as this number is greater than 1 minus square root of r, when r is larger than 1/4, so our construction beat the Johnson radius for the high rate. Second, moreover, we show that if we allow the field size Q to be even larger, say to be a double exponential power of n, so we are able to give an explicit construction of RS codes that can be decoded beyond Johnson radius. And this is the first explicit construction of such codes in the literature. Finally, our construction is tight, as we also prove the following singleton bound for this decoding, which states that the decoding radius rho cannot exceed L over L plus 1 times 1 minus R. So it is easy to say that if we let L equals 1, then this bound reduces to the singleton bound. And our code construction achieves this bound for L equals 2. Our second construction states that for large Q, almost all RS codes are 3/4 times 1 minus R, 3 least decodable. And it beats the Johnson bound for R larger than 1 over 9. And then we can also provide an explicit construction, and this bound is also tight because it achieves this singleton bound for L equals 3. So I will end this talk by mentioning a list of open problems and the list size equals 3. So first, is it in our construction, the field size Q is an exponential power of n. Is it necessary? Or it can be much smaller, say Q, say Q can be a polynomial function of n. Second, we only consider the combinatorial decodability of RS codes. But what about the algorithm? Does there exist an efficient algorithm that achieves our bounds? And finally, is this bound always tight for every positive integer L? So we know that it is true for L equals 1, 2, and 3. So my talk ends here, and thanks a lot for your attention.
Thank you. Thank you for being on time again. Any questions? Your question. Shahar, please talk.
Hi, yes. So I wonder, so you prove it for L being 2 and 3, and I wonder what's the conceptual difference between L being 2 and 3 and larger L?
Because for L equals 2, we have a very nice proof, and for L equals 3, we have a more complicated proof which uses induction. I think for L to be larger, say L equals 4 and 5. So the case maybe we can also prove this upper bound using induction, but there are too many cases, so we don't know how to reduce the number of cases in the induction. Yeah.
Maybe I'll add that and ask. Maybe you can say a few words about the approach. I think the approach is very original. It's not the usual approach for listing.
Okay, so. For example, where L equals 2, so we found that if the code does not satisfy this decodability, then it means that there exists some vector y such that the Hamming of radius of this radius and the center y contains at least 3 code words of the code. So you can imagine that there are 3 code words of a code that are contained in a small Hamming. So those 3 code words must have many equal coordinates. So then we found a method that transfers those combinatorial intersections to some algebraic dependencies. So yeah. So in other words, if we found the evaluation points of the little Solomon codes to be highly, in a sense, to be highly independent, then the code will satisfy this construction, will satisfy this condition. Yeah. So the basic idea is the polynomial method. Okay.
Shahar, is that okay?
Yeah, thank you.
Thank you. Salil was asking what is known for the whole field. So I took the liberty and say that it's known that you can do much beyond the Johnson bound. Is that right, John? When you have the whole field, when you don't function.
Yeah. Because
there you know that it's known that you can't get much beyond the Johnson bound.
Right, the work of Benson and Compati and
Benson, Compati and Radek Christian. Cool. Are there any disabled talking? Yeah. Okay, any other questions? Okay, cool. So let's move to the next speaker. Our next speaker will be Andrei. Can you unshare your slides?
Yep.
Our next speaker will be Andrei Ryazanov from Carnegie Mellon.
Yep.
Maybe I forgot to say our first speaker was also from Carnegie Mellon, and the second one was from Tel Aviv University. And will tell us about polar codes. Basically, I think these are the main questions about polar codes. Okay, please go ahead.
All right, thank you for the introduction, and thanks everyone for joining. Yeah, so this talk is going to be about polar codes with near optimal convergence to channel capacity, and this is a joint work with Venkat Goswami and Min. So the setup for us will be very standard channel coding in the Shannon model. So basically we have some communication, which might be corrupted by some noise, which is going to be stochastic noise. And we will model it by having a probabilistic coding channel in the middle of the communication. And the channel for us will be memoryless. So if we use it more than once, then every usage is completely independent. And we will restrict ourselves to binary input channels. So the input alphabet will be 0, 1 bits. And as usual, to mitigate the noise that the channel uses, we will use codes. So the code is a subset of f2 to the n, and we will actually restrict ourselves to linear codes. So linear code C is a linear subspace of f2 to the n, where we call n to be the block length. This is the actual number of times that we use the channel. The dimension of the subspace K is the dimension of the code, and we are interested in this rate R, which is fraction K over N over code, which corresponds to how efficient our communication is if we use this code. And of course, our goal is to have codes with this rate to be maximal possible. And there is a fundamental result by Shannon, which said that basically every channel W has a notion of capacity, IOW, which is a real number between 0 and 1, such that you can reliably communicate with codes with rates below the capacity, and reliable communication is not possible at rates above this capacity. And the next natural question then is, how do we actually construct and use codes which have rates close to this bound, to this capacity of the channel? So let's say we want the codes to have rates epsilon close to capacity. And moreover, we will need these codes to be somehow efficient. And in particular, we say that we want the block lengths of this code to be somehow bounded and small. So what Shannon actually proved is that if we use random linear codes, then it is possible to get the rates epsilon close to capacity if we only use the block lengths to be of order 1 over epsilon squared. And it was later shown to be the best optimal scaling. So basically, if you want to be epsilon close to capacity, you cannot have the block lengths smaller than 1 over epsilon squared. So random linear codes achieve this optimal scaling, but they are non-constructive and non-algorithmic. So we basically do not really have any decoding algorithms for them other than brute force, which is exponential time. And the natural challenge that arises from this is to construct explicit codes which approach capacity, so which have rates epsilon close to capacity, which will also have somehow bounded block length, and for which we can get efficient encoding and decoding procedures, where by efficient here, I mean something like polynomial in 1 over epsilon. And in our work, we resolve this challenge. So we prove a constructive, quantitatively strong version of Shannon's theorem. So we construct codes which have rates epsilon close to capacity, for which the block length scales almost optimally. So block length is almost quadratic in 1 over epsilon. And moreover, for these codes, we have this very fast and again encoding and decoding procedures. And the construction for these codes is polynomial time. So the previous, such kind of result was previously proven only for the case for the binary erasure channel, which is this channel which basically erases the input bit with some probability. But what we do is we prove this for arbitrary BMS channel, where BMS channel stands for binary input discrete memoryless symmetric channel. And this is just much more general and wider universe of channels. And for comparison, the previous best known result for these settings for arbitrary BMS channel achieved the scaling of block lengths being around 1 over epsilon to the power around 4.7, while here we prove the scaling of block lengths to be near optimal, near quadratic. So our codes are actually a variant of polar codes, which are the codes introduced by Arikan in 2008. But instead of explaining what polar codes are and how we tweak them to achieve this result, I will rather briefly explain what is the key technical ingredient that we use to prove our results, because it is of completely independent interest and it just concerns bit decoding of random linear codes. So in this picture, we just use a random linear code for communication. We have a message of k bits and we multiply it by a random matrix of size k by n. We obtain a code word, we send it through the channel and observe the output vector. So the task we're interested in is we try to decode the first bit of the message, just a single bit, given the output vector. So what we prove in our work is that if the rate of this code is slightly above capacity, if this fraction k over n is more than capacity by at least around 1 over square root n, then you cannot reliably predict even the first bit, the single bit of the message, if you know the output vector. So what we knew before and what follows from converse part of Shannon's theorem is that if you try to communicate at the rate above capacity, then predicting the whole message is not reliable. But what we prove is that you cannot even predict the single bit of the message much better than just flipping a coin. All right, so this is our key technical ingredient, and this is going to be it for me. I will bring back the main result on the screen, and thank you.
Thank you. Any questions? Okay, so I have a question. So maybe it's the same question as the first speaker. So it seems like you solved the main open questions about polar codes. Is there anything to do in anything left to solve in polar codes? Any algorithmic questions? Or?
Yeah, specifically one possible future direction is to improve the construction a little bit, because currently it might be seeming like a little too complicated. So for example,
simplify.
Yeah, so for example, in the regular polar codes, well, the construction is completely recursive and it uses one kernel throughout the whole construction. And what we did is we actually used completely different kernel, different matrices in the construction, and it kind of complicates all the construction a lot. And one possible direction would be to prove if to check if it's possible to get the construction with one single kernel. Yeah.
One kernel that works for all channels.
Yeah, exactly.
I see. Avishai is asking, do you think this can also work for Reed-Muller codes? I guess whether Reed-Muller codes also achieve the same scaling.
We didn't look at that at all. Yeah, I cannot say anything about that. Sorry.
What is known about Reed-Muller codes? Do they achieve with polynomial scaling for any BMS?
Actually, no.
I guess even that is not known.
The only family of codes for which the polynomial scaling is known is only polar codes, and yeah, it's still open if there are other families that achieve the same scaling. There are codes which are assumed to have the same scaling, but yeah, polar codes are the one for which it's proven.
So Avishai is saying that they achieve capacity for BEC. I also have such a recollection, but they don't have a polynomial scaling for BEC.
Sorry, Reed-Muller?
Reed-Muller codes for binary ratios channel?
That might be the case. I'm not really sure about that.
I see. Maybe only for BSC. Maybe it's even not known.
Yeah,
for it's not known that they achieve capacity even for general BSC.
Yeah, but for BSC case, it's much more
channel.
studied, and because it's a little bit more convenient.
I think it's just not known even for any channel.
Yeah.
And even for BSC, I'm not sure whether they achieve like polynomial dependency on epsilon. I'm not sure. Any other questions? Okay, cool. So now let's move to our last speaker, Raghuvant Saxena. And he will tell us about interactive coding.
Thank you. This paper is about interactive error resilience, and I will start by defining the setting under which interactive error resilience is studied. So you have a channel connecting two parties, Alice and Bob, and these two parties want to run a protocol pi over the channel. How will they run this protocol? If you assume that the channel between Alice and Bob is noiseless, which means that the messages sent by either of the parties are received directly by the other party, then the parties can simply execute pi by running it message by message. So for example, Alice may send the first message and Bob may send the second message and so on. What happens when the channel is noisy? A noisy channel is parameterized by a parameter theta and is such that a theta fraction of the symbols sent to the channel can be adversarially corrupted. This means that if the total number of symbols sent is t, then 1 minus theta times t of those symbols are received directly, but an adversarially chosen theta t symbols may be changed before they reach the other party. Over this noisy channel, because the symbols are corrupted, you cannot run pi by executing it bit by bit. Instead, what you need to do is you need to encode pi to a protocol C of pi. That would work even if a theta fraction of the symbols in C of pi are corrupted by the channel. Okay, overall, we get that if you want to run a protocol pi over a noisy channel, then you need to construct a code C and run C of pi that is resilient to a theta fraction of noise. And one can imagine that as the value theta of the noise becomes larger and larger, the task of constructing this code C becomes more and more difficult. And a natural question is, what is the largest value of theta for which there is a code that has error resilience theta, which means that this code C will work even if a theta fraction of the symbols sent over the channel are adversarially corrupted. This question was first considered in 1993 by Schulman, where he showed that this largest value theta of the interactive error resilience is at least a small constant. In 2011, Mart Triverman and Anup Rao showed that this value is actually, in fact, at least a quarter. Moreover, BR11 also showed that if your code C is restricted to be non-adaptive, then 1/4 is exactly the right answer. And no non-adaptive scheme can have an error resilience higher than 1/4. Therefore, the question after BR11 is whether there's an adaptive scheme that can do better. And in 2014, GHS, which is Mohsen Ghaffari, Bernard Hoppler, and Madhusudan, showed that indeed there is an adaptive scheme that has error resilience 2/7, strictly higher than 1/4. Even though this, even though the best known upper bound was 1/3, it was believed that 2/7 is the right answer, and no coding scheme can have error resilience strictly larger than 2/7, even if it is adaptive. We show that this is not the case, and in fact, there is a coding scheme with error resilience 7/24, higher than 2/7. This is the first scheme to break the 2/7 barrier, and it means that the error resilience of general adaptive schemes is strictly in between 7/24 and, is in between 7/24 and 1/3. In an upcoming work, we show that it is strictly in between and pin down this value to the exact constant. Okay, so this is the main result, and I'll now take 2 sentences to cover some of the techniques. For this, I would like to take you to the feedback channel, which is the same as the channel I described, except that over a feedback channel, the party that is sending the symbol knows whether or not it was interrupted. Because of this extra information, the feedback channel has a higher error resilience, and it is known that in fact that value is exactly 1/3. Our approach is that over the channel that has no feedback, we try to incorporate some aspects of a channel with feedback. We do not go all the way to a channel with perfect feedback, but whatever weak implementation we have of feedback over a channel lacking feedback allows us to improve the error resilience from 2/7 to what we get, which is 7/24. Thank you.
Thank you. Avishai was asking a question, which I again took the liberty to answer. He asked what is the exact constants. So I think in this paper you only show that it is at least 7/24.
That is right. In this paper, we show that it is at least 7/24. This number 1/3 is 8/24. The exact constants happens to be 7.5/24. And we show this in an upcoming work.
So in your full version of your talk, you mentioned that you solved, the exact constant.
Yeah.
So what is the exact constant?
It is 7.5/16 or 7.5/24.
I see. Okay, cool. Any other questions? Other questions? The one is the follow-up. Okay, so this was answered, right, Avishai? Yeah. Cool. Any other questions? See if there are other questions. Okay, I would like to ask more questions. So I think this was not also mentioned in the full version of the talk. Maybe you want to say what's the difference between adaptive and non-adaptive?
Oh yeah, that's a good question. So a coding scheme can have two types, adaptive or non-adaptive, and these are differentiated as follows. Suppose the scheme has T rounds, then for a non-adaptive simulation, even before the scheme starts, you know for all rounds 1 to T, which of the two parties is speaking in that round. So for example, you may know that in the first round, Alice is speaking, in the second round, Bob is speaking, and so on. For an adaptive simulation, you do not know that. And in fact, the identity of the speaker will depend on what communication is taking place before that round. This means that if in an adaptive protocol, a certain communication happens till round I, then maybe Alice speaks in round I+1. And if a different communication happens in the first I rounds, then maybe Bob is speaking in I+1. And therefore, the parties get more power to protect from more errors in an adaptive simulation.
Good, thank you. More questions? Actually, I'm also interested about the efficiency. Is this protocol efficient?
So
computationally efficient?
This code has a building block from a paper by Mart Braverman and Klim, which is dealing with list decoding under high errors. And that plot is not known to be efficient yet. But given that that is efficient, everything we build on top of it is efficient.
Is efficient.
Yeah.
Cool, thank you. Another question from Josh Cook. Does this hold also for quantum protocols?
I do not even know what quantum protocols are. I'm sorry, I cannot answer that.
I think this scheme is complicated enough. So adding quantum will even. So again, so given there's a new question by Gilles Bassard. In adaptive schemes, due to communication errors, you cannot prevent from wanting to talk. So what do you do if parties want to talk at the same time?
So we assume that if both the parties are speaking or none of the parties is speaking, then it is a free interruption to the adversary. So both the parties will receive some interrupted symbol and it will not be counted towards his budget even.
Okay, so I guess same questions for everyone. I mean, all these, of course, yeah, I know that's what you meant. Thank you. So yeah, I guess it's the same question for everyone because all these talks were amazing and just solved everything. So given your follow-up work that solved completely the constant, what do you think are good open problems? Is there anything left or?
Off the top of my head, one open problem that I can think of is in the follow-up work, we have a coding scheme that has the right error resilience, but our coding scheme has rate that is exponentially small. And one question is to get something that has, say, constant rate.
I see. It's only for a message exchange or something like that.
Yes, yeah. And that implies that for general tasks, it has an exponential be small rate.
I see, I see. So that's a good question. And also maybe efficiency.
Yeah.
Good. Any more questions? Okay, so thank you everyone. Stay safe and well, and I hope next STOC we meet in person, next conference. Okay, good. So I guess we can stop the recording and streaming. And if you want, we can hang out a few more minutes if you want to ask questions or another option.